Kirchhoff's rules give us rules for analyzing complex circuits and make it possible to analyze circuits where you have multiple branches with both resistors and batteries in them. The first thing you need to do in order to apply Kirchhoff's rules is to find all the junctions in your circuit. Remember, a junction is a place where a current either splits or comes back together. So it's where multiple wires join or branch off. In this circuit, there are two junctions at B and C, because these are places where multiple wires come together, and so currents either come together or split off. In this circuit, you can see there are 1, 2, 3, 4 different junctions. So the first step is always to identify the junctions. Then we choose one or more of these junctions to apply the junction rule to. The junction rule states that the sum of the currents entering a junction must equal the sum of the currents leaving a junction. This rule makes a lot of sense. If you have electrons coming into a junction, then the same number of electrons must leave a junction. So if you have a junction like this where a current is coming in and then splits into two, you would write down that I1, the current coming in, is equal to the sum of the currents going out. Likewise, in this circuit, we have one current coming in, we have two currents coming out. So you would say I, which is the current going in, is equal to the sum of the currents going out, I1 plus I2. Here we have a junction where there are two currents going in and one current going out. The sum of the currents going in is equal to the sum of the currents going out. Once you've written down a junction rule equation, then it's time to apply the loop rule. So with the loop rule, you take your finger and trace around any closed loop in the circuit. So a closed loop means you stop where you started. So this might be a closed loop, or you might go all the way around the circuit. As long as you come back to the place where you started, that is one closed loop. And it doesn't matter if you go clockwise or counterclockwise. The only important thing is that you stop where you started. While you are tracing around the closed loop, you're writing down potential differences for the components that you encounter, and then you set the sum of those equal to 0. So we have to remember the potential difference sign conventions that we use. If you encounter a resistor in your circuit and you're going with the current across the resistor, you write down plus the current times the resistance. If you're going across a resistor with your finger and you're going opposite the direction of the current, then you write down minus the current times the resistance. If you cross a battery and you hit the positive terminal first, you write down positive the voltage of the battery. If you go across a battery and you hit the negative terminal first, then you write down negative the potential difference of the battery. So here is how we use the rules. The first step is we find the junctions in a circuit. Then between the junctions, we label currents and pick current directions. Here the current directions and labels have been specified. So I1 goes from junction to junction, which currents always do. They always follow a branch which goes from junction to junction. So this would be I1. I2 goes from junction to junction along the top branch, and then I3 goes from junction to junction along the bottom branch. Sometimes the current directions and labels aren't given to you to start with, and in those cases you just have to pick. You just have to pick a current direction and label, and just be consistent when you write down your equations. If the current is actually flowing the other way, it's no big deal. You'll just get a negative answer for your current, which will agree with the picture that you've drawn. So once you have done that, once you have labeled the currents and picked current directions, then you can apply the junction rule to one of the junctions. Then trace around loops with your finger, writing down equations according to the loop rule, and to make sure you have as many equations as unknowns. So for this example, if we pick one of our junctions, if we pick this junction, and then apply the junction rule to it, we have two currents going in, one going out. So I1 plus I2, those are the currents going in, equals the current going out of this junction. So there's our junction rule equation. Then we can write down some loop rule equations. So for example, this first equation comes from going first through the 4 ohm resistor. So we're tracing around this upper loop. And first we go through the 4 ohm resistor. We're going with the current because I2 goes like this. So we're going with the current, so we write down positive 4 I2. Then we hit the positive terminal of the battery, so we write down plus 14. And then we go against I1. We go against the current through the 6 ohm resistor, so we write down minus 6 I1, positive terminal of the battery, plus 10 volts. And then we're back where we started, so the sum of those potential differences is equal to 0. Then we could also go around the outside of the loop. If we did that, we first pass through the 4 ohm resistor in the direction of the current, so that's plus 4 I2. We hit the positive terminal of the battery, plus 14 volts. And then the next thing we hit's a resistor. We're going with I3 through this resistor, so that's plus 2 I3. And now we're back to our starting point, so the sum of those potential differences is equal to 0. We could potentially do the same for the bottom loop. If we go clockwise, starting at B, we hit the negative terminal first, we would write down minus 10, and then we're going with the current, so that's 6 I1, and then we're going through this resistor here, so that's plus 2 I3 since we're going with the current, and then the sum of those is equal to 0. Now, if we were solving this problem, we would write down one junction rule, and then we would write down 2 of these 3 equations, and it doesn't matter which 2. We have 3 unknowns, so we need 3 equations, but we would not just write down 3 loop rule equations and then solve them, because it turns out that one of these 3 is redundant. It's something called, it's not linearly independent of the other 2, which just means you could do math with the other 2 to come up with the third one. It doesn't add additional information. And so if you tried solving these 3 equations using just these 3 equations to solve for I1, I2, and I3, then you would get the very useful information that 0 is equal to 0. You'd get everything canceling out, which isn't very helpful. So you do need the loop rule equation, and then any 2 of these you get the junction rule equation and then any 2 of these 3 loop rule equations, and then you can solve the problem. So typically what you do is you write down, if you have a pair of junctions, you write down a junction rule for one of them, and then you write down enough loop rule equations so that you have as many equations as you have unknowns. So once you have the equations that you need, you can solve them for your unknowns and then check your solution at this website. So this is a Kirchhoff's law equation solver. And you can check to see that this gives you the same numbers, because when you solve the equations for your unknowns, that will take a bit of math, and it's pretty easy to make an algebra mistake somewhere. All right, so next let's look at this question and this little circuit with the currents that are labeled. So which of the following would not result as an application of the loop rule?